It's my pleasure to introduce the Maryland crew with Chris being the first speaker.
Thank you very much, Dave. It's a real pleasure to be here. So the title of my talk, as you see, is Thermodynamics at the Nanoscale. And what I'm going to try to do is present a fairly brief and reasonably pedagogical overview of some progress that's been going on over the past couple of decades in basic non-equilibrium statistical physics. So my talk is really going to focus much more on the physics side of things than on anything to do with life sciences per se, but I hope you find it interesting. So let me begin with a slide that places this talk in some perspective. As we all know, the laws of thermodynamics were originally written down to describe the behavior of macroscopic machines, notably the steam engine depicted on the left over here. Whereas these days, there's a great deal of interest in understanding the precise the behavior of microscopic machines, such as the ATP synthase depicted on the right over here. And as many of you probably know much better than I do, the ATP synthase is an exquisite biomolecular machine that exists in the mitochondria in each of our cells. And basically, it takes advantage of a proton gradient across a membrane, or equivalently, a chemical potential difference, to generate torque. This torque then gives rise to mechanical motion, and that mechanical motion in turn leads to the synthesis of ATP from ADP and inorganic phosphate. So effectively, this thing is continually recharging the cells, recharging the batteries in the cells of our body. Now, even though the ATP synthase and the steam engine are separated by something like 8 orders of magnitude in length scale, ultimately each one of these operates by taking advantage of some sort of thermodynamic free energy, either a temperature difference in the case of the steam engine or a chemical potential difference in the case of the ATP synthase, and using that free energy to generate some work, mechanical work or ultimately chemical work in this case. So in view of this kind of similarity, it's somewhat natural to ask, how do the laws of thermodynamics, laws that were originally written down to describe steam engines, how and to what extent and in what form do those laws apply to microscopic systems like the ATP synthase? Or more succinctly, what do the laws of thermodynamics look like at the nanoscale? Now, in this talk, I'm not going to try to give a general answer to that question, which is a very broad one. Instead, I'm going to focus specifically on the second law of thermodynamics and how it applies to systems that are being driven away from a state of thermal equilibrium. And kind of the main takeaway message, the take-home message of my talk is that when fluctuations are properly accounted for, then the inequalities that we ordinarily associate with the second law of thermodynamics can be recast as equalities. And throughout this talk, when talking about the second law in particular, I'll have in mind specifically the relationship between work and free energy for a system that's driven away from an initial state of thermal equilibrium. So let me remind you first about that relationship using my favorite pedagogical example, a stretched rubber band. So imagine I take an ordinary rubber band surrounded by a room full of air. I attach one end of the rubber band to a fixed wall, the other end to an ideal spring, and this is me at the far end of the spring, kind of pulling with all my might, trying to stretch the rubber band. I'm going to let lambda denote the distance from the fixed wall to the far end of the spring. And I'll think of lambda as a thermodynamic work parameter. So this is some variable that I control directly, and I use that variable to act on the system of interest. So again, here we have a system of interest, that's the rubber band attached to the spring. We have a thermal environment, that's the surrounding air, and we have a work parameter, lambda. So with these elements, let's subject this system to kind of a textbook thermodynamic process. I start in the equilibrium state at the initial value lambda equals A. I then stretch the rubber band by changing the value of lambda from A to some larger value, lambda equals B. And I imagine that I do this relatively quickly and violently. So the system gets driven away from equilibrium. During this stage, I perform a certain amount of work on the system when stretching the rubber band. And at the end, let me imagine that I hold my work parameter fixed and I allow the system to come to a new state of thermal equilibrium. So I've got a process where I begin in one state of equilibrium A, I end in another state of equilibrium B. At intermediate times, I drive the system away from equilibrium and I perform some work on the system. In this case, the Clausius inequality applies. This is a classic statement of the second law. Ordinarily, as you'll remember from introductory thermodynamics, this is written ordinarily as a relationship between heat and entropy changes. But after one or two lines, one can recast this into the following form that's very convenient for our purposes here, which states that the work I do in stretching the rubber band from state A to state B must be greater than or equal to the free energy difference, delta F, between the initial and the final equilibrium state. And in fact, I'll get the equality here only in the limiting case where I carry out this process reversibly. All right, let's now look at a microscopic analog of stretching a rubber band, and this is offered by a single molecule Poet experiment. So schematically, imagine I take a single piece of DNA, I use some fancy chemistry to attach the two ends of this strand to two microscopic polystyrene beads. This gives me a kind of floppy dumbbell. I immerse this dumbbell in water, and now I grab one of the beads using a micro pipette, tiny suction device, and I grab the other bead using a laser trapper, so-called optical tweezers. And now imagine I'll let the lambda denote the distance from the far end of the micro pipette, which is fixed to the center of the laser trap. And once again, this is a work parameter that I can control. So I have a thermodynamic work parameter, lambda. I have a system of interest, that's the RNA strand attached to the two beads. And I have a thermal reservoir, which in this case is the surrounding water. And with these elements, let me again imagine subjecting the system to a process analogous to the one described with the rubber band, where those transparencies go. So I begin in a state of equilibrium corresponding to lambda equals A. I then stretch the molecule by changing lambda from A to B. This drives it away from equilibrium. Work is performed, and at the end, I let the molecule relax to a new equilibrium state. And now imagine that I go back and repeat this process over and over again, in principle, infinitely many times. Because this is a very small system, fluctuations now become very important. And what I mean by that is each time I repeat the experiment, the atoms that make up the system of interest, as well as the surrounding molecule, are moving differently from one repetition of the experiment to the next. As a result, the precise amount of work I perform from one realization to the next is going to be different. And because this is a very small system, these differences in the work, these fluctuations, are going to be substantial when compared, let's say, or can be substantial when compared to the average work that I'm performing. Okay? So in this case, fluctuations are now important. We can't ignore them, although we still would expect that the average work that's performed on the rubber band stretching should be greater than or equal to the free energy difference in accordance with the second law of thermodynamics. So this gives rise to kind of following semi-quantitative or heuristic picture. In a macroscopic case, each time we stretch the rubber band, we get exactly the same amount of work, and that work is going to be greater than the free energy difference, delta F, if this process is being carried out away from equilibrium. In the case of the single molecule, if we stretch it many, many times, we'll get different values of work each time. Rho of W here is meant to represent schematically the difference, or the histogram of all those work values over many repetitions. And now the second law suggests that the mean work should be greater than the free energy difference, delta F. But now we have substantial fluctuations. In fact, every once in a while, if we perform the experiment carefully enough, we might observe value of work down in this lower left tail over here, less than the free energy difference, delta F. This is something that would be absolutely shocking if we saw it in a macroscopic system. It would be a violation of the second law. In a microscopic system like this, it's not so surprising. It just comes from the fact that we're dealing with a very small system where fluctuations become important. Okay, so I think this kind of general picture was already well appreciated well more than a century ago by people like Maxwell and Boltzmann and Gibbs, who understood that the second law of thermodynamics really should be interpreted statistically. It's a statement about averages, and there are going to be can be substantial fluctuations around those averages when dealing with small systems. So what's new here? Well, it turns out that these fluctuations around the average are not just kind of boring random noise. Instead, they're a lot more interesting than one might suspect, and they're more interesting and more informative than one might expect. In particular, these fluctuations in the work satisfy a number of strong, potentially useful, and unexpected laws. By unexpected, I just mean these are laws that one would not have naturally just guessed by starting with a good understanding of macroscopic thermodynamics and scaling down to very, very small systems. So I'm going to discuss 2 or 3 of these laws, time permitting, during my talk. So the first one is this non-equilibrium work relation, which appears here. And this states the following. Let's imagine that if, instead of looking at the mean of this distribution, the average work, let's look at the average of the quantity e to the minus beta w over this distribution of work values. Here, w again is the work that's performed during one realization of the process. Beta is the inverse temperature of the surrounding thermal reservoir, and that remains well defined even if the system is being driven away from equilibrium. And delta F, as before, is the free energy difference between the initial and final equilibrium states of the system. So the claim is that this particular average, e to the minus beta w, is going to be equal to e to the minus beta f. Moreover, the claim states that this is true regardless of how close to or far from equilibrium the system remains during the process. So if you think about it, this places a fairly strong constraint on this distribution of work values. You see, this distribution rho of w, the shape of that distribution will depend significantly on how we carry out the process. If we carry out the process very, very slowly, then we would expect that this rho of w should be very sharply peaked, close to delta f. Whereas if we carry out the process very rapidly, we expect a much broader distribution of work values. But the claim is, no matter how we carry out, slowly or rapidly, this particular average, the integral of rho times e to the minus beta w, the value of that average is going to be determined only by the initial and final equilibrium states of the system, because those define the free energy difference delta F. So in some sense, this is analogous to a very familiar statement from macroscopic thermodynamics, which tells us that for any reversible and isothermal process from some state A to some state B, the work we do in getting from A to B doesn't depend on the path we take or how we carry out the process, as long as it's reversible. So this, in some sense, this work relation, in some sense, generalizes that statement to irreversible processes, provided we're dealing with a system that's small enough that we have access to these fluctuations that will allow us to calculate the average. Okay. All right. Before going on to the next prediction I wanted to talk about, let me first briefly discuss how this relates to the second law of thermodynamics. So here we have the non-equilibrium work relation. It's stated as an equality. This inequality over here is Jensen's inequality. This is a mathematical result that says for any real variable x, the average of e to the x must be greater than or equal to e to the average of x. This is just due to the fact that the exponential is convex. So this is entirely analogous to say the average of x squared must be greater than or equal to the average of x quantity squared. If we combine these 2 results, take the log of both sides of the equation, then after one or 2 lines, we arrive at this inequality, that the mean work must be greater than the free energy difference delta F. And this is, of course, just the Clausius inequality applied to microscopic systems. So this is nice. It tells us that this non-equilibrium work relation, which is an equality, implies something that we already knew, which is the Clausius inequality. So at least it's consistent with the second law. But it turns out we can do better than this. So instead of just asking about the averages, let me pose the following question. What is the probability that the second law will be, so to speak, violated by at least zeta units of energy? And let me explain what I mean by saying violated here in quotes. This picture over here shows the far left tail. This is just the far left tail of this work distribution over here. So this is that portion of the work distribution where the work is less than the free energy difference delta F, where in some sense it's against what the second law of thermodynamics would predict. And all I'm asking in this question is the following. If I carry out this experiment once, in other words, effectively if I sample one value of W from this distribution, what's the probability that the value I get is going to be less than or equal to delta F minus zeta, where zeta is an arbitrary parameter with units of energy? In other words, what's the area underneath this red portion of the curve over here? Well, we can calculate that. So this probability, the probability that W is less than delta F minus zeta, the area underneath this portion of the curve, is the integral from minus infinity up to this point delta f minus zeta of the distribution, rho of w. This, in turn, is less than or equal to the same integral, but now I've thrown in a factor here, e to the beta delta f minus zeta minus w. And the reason why this is an inequality can easily be seen. This factor that I've thrown in here, delta f minus, e to the beta delta f minus zeta minus w, that factor is greater than unity over the entire range of integration over here. Okay, let me now pull out this constant, e to the beta delta f minus zeta, outside of the integral. Let me extend the upper range of the integration to plus infinity. So this gives me, again, another inequality over here. And what I see now is that the integral here is just the average of e to the minus beta w. And that's equal to e to the minus beta delta f. So the bottom line is the delta f's here cancel, and after the dust settles, we get that the probability of observing a violation by at least zeta units of energy, that probability is no greater than e to the minus zeta over kt. In other words, this tail here decays exponentially or faster in this thermodynamically forbidden region. It's kind of analogous to a quantum mechanical wave function that decays in a classically forbidden region. So it tells us that if we carry out the experiment carefully, and depending on the size of the system and the experiment itself, we may observe these violations of the second law by 2 or 3 kt, because ultimately e to the minus 3 is not such a small number. But we have no hope whatsoever of observing a violation of the second law by 100 kt. Even though 100 kt on the macroscopic scale is still a very, very small amount of energy, e to the minus 100 is a fantastically small number. So this puts a very stringent upper bound on the probability of observing these so-called violations. And this kind of type down, I think, would have been difficult to get directly from macroscopic arguments. Okay, let me move on to the next prediction that I wanted to discuss, and this involves thermodynamic cycles. So let me use the term forward process to refer to the process that I've been discussing so far, where I imagine changing some work parameter from A to B, like stretching the rubber band. And I'll use the subscript F to denote forward. The reverse process is the one where I start in state B, and then let's say I contract the rubber band by changing lambda from B back to A. And I'll assume that whatever schedule I used in the forward process, I use exactly the opposite schedule for the reverse process. And I'll use R to denote, the subscript R to denote the reverse process. Each of these is a perfectly valid thermodynamic process. Each of these satisfies the Clausius inequality as shown over here. The minus sign over here is just for the fact that I've changed what I mean by the initial and the final state of my process. So we can represent these two inequalities as shown over here. And the interpretation is the following. The work that I do when I stretch the rubber band must be greater than the free energy difference delta F between the initial and final states. And this, in turn, is going to be greater than or equal to minus WR, which I can interpret as the work that I get back from the rubber band when I allow it to contract. So if I now think of an entire cycle where I stretch it and then contract it, these two inequalities immediately imply that the total work over the entire cycle must be greater than 0. And this is just a Kelvin-Planck statement of the second law of thermodynamics. It's a kind of no free lunch statement. If the inequality here were the other way around, then I could just stretch and contract the rubber band all day long and have a really wonderful source of energy. Because what I'd be doing in this process is effectively harvesting the energy from the surrounding thermal environment in the form of heat and converting that heat into work. And of course, the second law says that's absolutely forbidden. So again, it's a kind of no free lunch theorem. All right, let's think about how this might apply to single molecule pulling experiments. Let's imagine that I have my setup as shown over here. I stretch the molecule, allow it to come to equilibrium, contract it, allow it to come to equilibrium, and so forth, and carry out many repetitions of this cycle. During each repetition, I measure the amount of work that I did stretching the molecule. I measure the amount of work I get back when contracting the molecule. And at the end of the day, I plot these two histograms, rho forward of W, rho R minus W. And again, we expect that the means of these distributions should be in agreement with the predictions of the second law of thermodynamics. So that's shown over here. The mean of the red distribution is greater than delta F, and that's greater than the mean of the blue distribution. So those two spikes that you saw in the previous transparency now just acquire some finite width. And now the Kelvin-Plonk statement just tells us that on average, during a given repetition, the amount of work that we do on the process is going to be greater than or equal to 0. But again, if we do this process sufficiently many times, maybe every once in a while, we will see realizations during which we get back more work than we actually put in to stretch the molecule. So there's no free lunch on average. And again, as in the previous case, it turns out that these distributions are a lot more interesting than what might appear to be the case at first glance. So in particular, Crookes showed back in 1999 that the ratio of these two distributions, rho f of w divided by rho r of w, so the ratio of the red over the blue at any point w along this axis, is given by a very simple result. It's e to the beta times w minus delta f. And again, all of the symbols here, w, f, beta, and so forth, are the same as I've been discussing previously. So there's this very, very nice symmetry kind of between the forward and reverse work distributions. And again, the claim is that this remains true even if the system is driven substantially far from equilibrium during the process. One kind of cute consequence of this prediction is it says that these two distributions will cross exactly at delta f, because when w is equal to delta f, the right side of this equation is unity, and then the two distributions are equal to one another. So let me briefly go through an experimental test that was done, that was carried out to test this prediction. So this involved the kind of stretching and contraction single molecule pulling experiment that I've described. This figure down here shows basically the raw data, so to speak, coming from the experiment. So on the horizontal axis is the extension of the molecule. On the vertical axis is the force that's exerted by the laser beam on this bead that's trapped here. And the orange and blue curves correspond to the stretching and contraction parts of the process. And without going into too much detail, you see that there's this kind of jagged, in the orange case, you get these kind of jagged lines over here, similarly to a lesser extent in the blue case. And what's happening here can be easily interpreted. You see this molecule in its native state is folded into a hairpin fold. So when you start stretching it, at some point it pops open. It doesn't zip open gradually, it just pops open very suddenly. And when it pops open, the length increases suddenly and the tension decreases suddenly. So you get these lines. The other thing to notice about this figure is that the placement of these lines for the forward process, the orange lines, is significantly different from the placement in the reverse process, the blue lines. And what that's telling us is that the system is behaving differently when we stretch it than when we contract it. And this is an example of hysteresis. And ultimately, this is an example of the second law of thermodynamics manifesting itself in a very, very small system. So for this system, the experimentalists basically carried out many repetitions of stretching and contraction, and they came up with the work distribution. So those are shown in this right figure over here. I'm not sure how well they show up. The two purple distributions are the unfolding and refolding, or forward and reverse work distributions for the wild type molecule, and then the two yellow or gold distributions that are also shown over here are the corresponding distributions for a mutant molecule. So let me just emphasize that these pairs of distributions, like the purple one here or the gold one here, are really the experimental analogs of these kind of schematic distributions that I had shown over here. And now, in order to test this prediction, we have to have data in some region where the two distributions overlap. And so for the wild type molecule, you see that there just wasn't enough data to make that test. Whereas for the mutant molecule, it's not, the statistics aren't great, but there's this little region over here where the two tails overlap. And the inset here shows within that region, so within a range from 155 to 160. What's plotted on the horizontal axis is the work in units of kT, and on the vertical axis is the natural logarithm of the left side of this equation. So according to Crookes' prediction, the points should lie along a straight line whose slope is unity. And this experiment, the best linear, gave a slope of 1.06, which was well within the experimental error. So this experiment gave the first experimental confirmation, or sort of first experimental results that were consistent with this prediction. And in fact, a few years earlier, there had been other experiments testing the non-equilibrium work relation, which were also consistent with that prediction. In the time since then, many, many more experiments have been done, not just with single molecules, but with a variety of systems, like single trap beads, torsional pendulums, single electron boxes in kind of a solid state setting, and more recently, the quantum mechanics. There have been experiments that have looked at quantum mechanical versions of these predictions. I'm not going to go into any of the other experiments in any detail because my time is running short, but to date, all of the experiments that have been done have been in agreement with the theoretical predictions. So I would say that it's fair to say that there's a reasonably good body of experimental evidence that's in agreement with these predictions. There haven't been any experiments that have been out, that have disagreed with the predictions. Okay, there was one more result that I wanted to talk about, and this one is actually a little bit more abstract, but in my mind it's very cool because it kind of relates nicely to the path integral formulation of quantum mechanics. But my time is running short, and let me, instead of doing that, let me just flash the final result over here. That's not going to really make much sense if I don't go through the explanation. But probably the nicest explanation of this result is in a very beautiful paper by Gerhard Hummer and Attila Szabo that appeared in the NAS in 2001. And they argued that these sort of non-equilibrium results could be very useful in constructing free energy landscapes for biomolecular molecules, either in the computational setting or in the actual experimental setting. So I highly urge you to look at that paper there. Okay, so in the few minutes that I have left, let me go through one more topic that's related to these results. And this takes us actually a little bit further away from life sciences and maybe closer to philosophy. But it has to do with how these results relate to the so-called thermodynamic arrow of time. And the easiest way that I have to present this is in the form of a hypothetical thought experiment. So suppose that I show you a movie, and in that movie you see one of these forward processes being carried out. So for instance, you see a movie where a single molecule is being stretched. And in the spirit of a thought experiment, let's say that you have access to all of the microscopic details in the movie. So you can see how every single atom is moving around as a function of time, and so forth. And now you have the following task. You're given the following task. Shown this movie, since you've seen this movie, you should determine whether the events that you're viewing, whether you're viewing them in the sequence in which they actually happen, or whether I'm playing the movie backward for you. In other words, did I actually stretch a molecule and then show you the movie, which is what I'm telling you I did? Or am I trying to be tricky? Am I trying to deceive you? Did I actually contract the molecule and I'm just showing the movie to you run backwards? So you're supposed to take the best guess based on all the microscopic information that you have available to you, which of those is the more likely. And it turns out this can be analyzed quantitatively as a problem in statistical inference. And you set it up this way. You say that there are two hypotheses. So you have two hypotheses. One, which I'll denote by F, was that the forward process was carried out. In other words, the molecule was actually stretched. And the other hypothesis, R, was that the molecule was contracted, and now I'm trying to deceive you by running the movie backward. And so it turns out, and I'm not going to go through the details of the derivation, it turns out that the one piece of data that you need from this movie to help you make the best guess as to which hypothesis is correct is the amount of work that's done on the molecule in the movie. So let's say you look at how all the atoms are moving. From that information, you calculate how much work was done in the movie, in the process that you're seeing in this movie. Once you've calculated that value, no further microscopic information can give you any edge, any statistical edge in getting the correct answer. Moreover, there's a very simple formula that tells you what the likelihood of each hypothesis was given the data. In other words, given the amount of work that you see performed in the movie. And that formula is shown here. It says the likelihood that the forward process was carried out, in other words, the molecule was stretched, given this amount of work, W, observed in the movie, is given by this formula over here. It's 1 divided by 1 plus e to the minus beta W minus delta F. The likelihood for the reverse process is just 1 minus this quantity. And we all know what this looks like. This is the logistic function. It's plotted over here. So this is telling us that when the work is much greater than the free energy difference delta F in many units of kT, then the likelihood that the forward process was carried out is very close to unity. And this makes sense, because if we see a process where the work is much greater than the free energy difference, then that process is very much in agreement with the second law of thermodynamics, so probably we're seeing things in the right chronological sequence. By contrast, if we observe a value of work that's much less than delta F, then this likelihood, this formula gives us a value here that's very close to 0. And again, that's very much in line with what we'd expect. If we see a work value much less than delta F, that's a big violation of the second law. Chances are the movie is being run backward. Okay? It's kind of like if you see a movie where an egg kind of unbreaks itself, then you know the movie is being run backward. So this is, once again, this is very much, I should say, there's this transition region whose width is about a kT or so, or a few kT, over which it's hard to, over which it becomes difficult to say with certainty which process was carried out. So again, all of this is consistent with what we would have guessed from macroscopic thermodynamics. But what I find really remarkable about this result is that it's completely independent of what kind of system we're carrying out, how slowly or quickly the process is being carried out, or in other words, how close or far from equilibrium we are. This is really a universal process, a universal result within the context of these kinds of forward and reverse isothermal processes. So this result was first derived by Michael Schertz and colleagues, later in a somewhat different manner by Paul Maragakis, but this was in a somewhat different context from the one that I'm presenting here today. Okay, so let me just, since I'm already a couple minutes over time, let me just summarize by repeating the take-home message of this talk, namely that if fluctuations are properly accounted for, then the inequalities that we ordinarily associate with the second law of thermodynamics as applied to macroscopic systems like stretching the rubber band, these inequalities can be rewritten in the form of equalities. And I've talked about 2 of them in some detail, didn't really have a chance to talk much about the third of these results. If you want to follow up on any of this, let me kind of shamelessly plug my review article from several years ago. And with that, I'll thank you for your attention. I'll be happy to take any questions.
Thanks for a very nice talk. This was very clear. So I understand that, I guess, this sort of hypothesis testing example was more for pedagogical enlightenment. But I then wonder, how would you tell the free energy difference from watching the movie? You would need to know delta F, right?
Yes, absolutely.
Usually we want to know delta F, we don't know.
Absolutely, I should maybe emphasize in this very much pedagogical setting, where I really was aimed at talking about the error of time, I assumed, I should have been explicit, I assumed that you knew delta F ahead of time. In these papers, they take the opposite. So these papers were actually in the context of free energy calculations or free energy extraction methods. And basically here they assumed that delta F is not known, but they found that this kind of result is useful in helping to determine what the most likely value of delta F is, given the work that you observe in the experiment or in numerical simulations.
Hi, Chris. So, in theory, we need infinitely many realizations, right?
In theory, infinitely many, yeah.
And since we are looking for the regular ones that contribute most to exponential average, there's a convergence problem.
Correct.
So comparing Crookes fluctuations and your locality, which one converges faster, or is it?
Well, okay. So first of all, you should always expect if you're using information from both the forward and the reverse distributions, you should expect to converge faster. So Crookes' result it's not typically used directly to calculate delta F, because this is a statement about 2 distributions. So for instance, looking at where they cross is not a particularly efficient way of doing that. So given the forward and reverse work distributions, the most efficient way to estimate delta F is by using what's called the Bennett's acceptance ratio method, which is something that Charles Bennett developed many years ago in an equilibrium context, where it's actually similar equalities apply. And Bennett showed that that was the most efficient way to estimate the free energy difference. Having said that, if these two distributions don't overlap very much, then there's really not much you're going to do. It's not going to converge very well. So in some sense, this prediction, in terms of efficiency, this prediction will break down a little bit earlier than this prediction combined with Bennett's results. But if you're doing things far away from equilibrium, neither of these two is going to be practical, so you have to use some other tricks. And there are a number of other tricks that you can use, mostly relying on breaking down your problem into a bunch of smaller pieces, and then each of these converges a lot better.
Thank you.
Thanks.
So this was a wonderful talk, but maybe you can help me on some practical problems. You showed your ATP science at the beginning, but you never went back to it. So let's try to go back to the big machines. The problem I have these days is, how do I even know if I'm converging? So basically, when people run simulations of these things on fast runs, my experience by different other method experiments is basically they're missing major fluctuations of the protein, so what they're getting are very large entropic barriers.
Yeah.
Instead of the real physical one. But if I keep on running fast simulations, I'll never see this entropic part of it that they may give the appearance of convergence. And then, do I have no hope, or is there a way I can actually figure out, maybe by just using your estimates, that I'm really out the ballpark? Because I think most simulations are bluntly wrong these days, and people don't even notice.
Yeah, that's true. So there's a number of things. So first of all, in some sense, the easiest thing to do would be run both forward and reverse simulations and look at the histograms and see by eye, are these anywhere close to crossing? If they're very far from crossing, don't try any methods. Nothing's going to work. You have to break the problem down into smaller pieces. On the other hand, if they do cross somewhat, then typically what you find when applying, let's say, this result over here, typically what you find is that when plotted in terms of the increasing number of samples, the thing seems to be converging, and all of a sudden the estimate for free energy drops down. And it seems to be converging, and then all of a sudden, and so that's an example that it's converging but slowly. And there has been also work on kind of what the best practices are in trying to determine whether you've converged or not. But I think the simplest rule is do both the forward and reverse work distributions, and at least get, because that might tell you that you're way out of the ballpark and forget it.
Chris, thanks a lot for a very clear talk.
Thank you, Dave.